is going to be dedicated to discuss the part 2 of fundamental memory concepts as a part of the model 3 memory system of computer organization. In the previous discussion we have discussed the concept of very fundamental memory, that internal organization of the memory layouts, memory architecture, and dynamic and random access memory cells. Continuation of this going to be discussed in detail about this, how to organize the memory, right? So going to be here. So the presentation milestones are memory organization, asynchronous dynamic random access memory, synchronous one, static random access memory, read-only memory, and so on. That is coming to this asynchronous dynamic random access memory. So let's consider design of this dynamic random access memory of 2 MB, right? 2 MB means, so that is 2 power 10 is a 1 kilobyte, so on that 2 power 20 is a 1 MB, 2 power 20 is equal to be 1 MB, 2 power 21 is a 2 MB, right? So 21 address lines is needed here to uniquely identify the 2 MB memory locations. So total of 21 bit address will be there, right? It required total of 21 bit address lines will be essential to organize that memory, that is. So here we can observe that is a using 4K into 4K, using 4K into 4K memory will be there, that is. So this 4K can organize, that is with help of the each row can store 512 bytes, that 512 bytes. So that select a row and 9 bits for the group, 9 bits for the group. So we can have that 45, the total 21 address lines will be there. So those 21 address lines we can have that split into row address and column address. So that is a row address. So since this is a dynamic random access memory, so we can make it into that is a the row address strobe and column address strobe, that is. So column address strobe we have, that is the column address strobe will be help us to decode, that is column address latch, that is. So row address decoder will be there. So we can have that cell array we can formulate, that is. So after formulating, that is 55. Okay, so sensor read circuit will be there. So this sensor read circuit will drive out the information from that cell, that is a total memory is a 4096 into 512 into 8. So the available chip is 512 into 8. This is a chip is available. So this we can have multiply with the 4K. So we'll get a 2 MB. So total 2 MB memory. Each row can store 512 bytes and 12 bits of address. 9 bits selects for the that row, that is, right? So we have D0 to D7 is the data in and data out, right? So data in, data out. So total first apply the row address will be there, and go to the decoder and reaches to the memory. So that latches the address, then apply the column address. So column address will be there. So the cache, that is a column address signal, latches the address, column address signal, that is active low, latches the signal. The timing of the memory unit is controlled by specialized unit which generates the row address and column address. Row address and column address. So the timing memory unit by this row address and column address are helpful. So the fast page mode. So the suppose the what we want to access the consecutive bytes in the selected row, consecutive memory, consecutive bytes in a selected row. This can be performed without having to reselect the row. This can perform without having to reselect the row. The row can perform. Add a latch at the output of the sense circuit in each row. Add a latch at the output of the sense circuit. All the latches are loaded when the row is selected. All the latches are loaded when the row is selected. So different column address can be applied to select and place the different bytes on the data lines. Different bytes on the data lines. Consecutive sequence of column address can be applied under the control signal cache without reselecting the row. Consecutive sequence of column address can be applied under the control without, that is, allows the block of data to be transferred, allow the block of data to be transferred at much faster rate than the random access. Much faster rate. A small group of bytes is usually referred to as a block. So block, memory deals in terms of the blocks, where processor deals in terms of the bytes or words, right? So this terminology will be involved. This transfer capability is referred to as a fast phase mode. This kind of transfer phase, it is a fast phase mode, that is. So synchronous decorum continuation. Operations is directly synchronized with the processor clock signal. These memory operations are try to synchronize, match that speed with the processor speed, that is a clock signal. So output of these sense circuits are connected to latch. Output will be connected to latch, that is. So that is a row and column address that will be split into row address and column address, right? So row address, the given address we have discussed previous slide. So the total address generated by the processor, that going to be split into row and column address. So that similarly is a latch will be performed. So after latch there is a decoder. Decoder we have discussed about decoder and column decoder. So both will decode this address and possible to explore all the memory cells of the memory set. There is a cell array and here attached to read and write circuit and latches, right? So there is a read and write circuit will be there. So this read and write circuit will with help of the read and write control signal or chip selection, from this it will activate the corresponding row in order to drive out the information or put into the information. So from the read write circuit we have the input and output. So data in register will be there. So there is a buffer. So data coming from this serial or parallel port, and it will be asked that to sit here in the buffer, and at the time comes it will be enter, it rush to the memory. Similarly, when you read some data from the memory, that will be get passed here and it will be asked to sit in the buffer. So that is called data output register. So during the read operation, the contents of the cell in a row are loaded onto the latches. So loaded onto the latches, that data, and there is a refresh counter. refresh counter. So we have discussed in length that basic dynamic random access cell which contains a transistor and capacitor. So capacitor even after power no power, then capacitor try to conduct some power with help of the residuals. So that will be maintained to certain amount of time. After that it will be stop. So stop means we may lose the data. So in other words, to avoid this losing of data, we need to be give some power. So how we can give that power? By refreshing. So refresh counter will be there. So we can add after every nanoseconds the refresh will be taken place. So that data will be resonate. So data will be maintained there. During the refresh operation, the content of the cell are refreshed without changing the contents of the latches. So without losing that information, that the refresh will be happening, that is. So the data will be on out. The data will be out. So there is a register, mode and register, and timing controls will be there. This entire memory. So there is a row address strobe, column address strobe, signal will be there, and clock is put it into this chip. That is a read and write per control signal and chip selection control signals. So data held in the latches correspond to the selected column are transferred to output. Data held in the latches correspond to the selected columns are transferred to output. So for the burst mode of operation, so successive columns are selected using the column address counter, and clock. So burst mode of transfer, so we have discussed in length in the DMA controller. So DMA will be send the data burst mode or block mode, right? So it will be send few words at a time instead of block. So that is a burst mode of operation. Successive columns are selected using the column address and the counter and clock address counter. So that is what is called the column address strobe signal need not be generated externally. So a new data is placed during the rising edge of the clock pulse. So the data will be transferred rising edge of the clock pulse, and every clock pulse, that too rising edge of the clock pulse is most important. During that time it will be transferred. During that time it will the decodation and various other timing aspects will be there. So that is a single transfer. So the latency, bandwidth, and that is a DDR SDR RAMs. So latency, it is a memory how much amount of time the initiated the memory operation and completion. So initiation and completion is a latency time. Bandwidth, how much amount of data transferring and receiving. So the bandwidth is a capacity of the channel. And the DDR SDR, so DDR is a data double rate synchronous dynamic random access memory. So the normally we have seen that SDR, the single data rate. So that single data rate going to be achieved with help of the rising edge of the clock pulse. So for every rising edge of the clock pulse, that data will be transferred. So that memory latency is the time it takes to transfer the word of data to or from memory, right? So that is a amount of data going to be the time is required to transfer the data, that is called latency. So memory bandwidth is the number of bits or bytes that can be transferred in a one second. So how much amount of data will be transferred in 1 second or received. So that is called bandwidth. So DDR SDR is a data double rate cell array is organized in two banks. Cell array is organized in two banks. So one bank will be transferred the data during a rising edge of the clock pulse. the other bank will be transfer the falling edge of the clock pulse. So every rising and falling, that will be a double. So data double rate. If it is only happen during the rising edge of the clock pulse, that will be SDR, single data rate, right? So the rising edge and falling edge, so that by that time it will be decoded the address, and every the action of this clock pulse is going to be dedicated to transfer the data. So DDR SDR internally perform double width access, right? So they perform the double width accesses at the clock rate and uses the double data rate interface to transfer one half on each clock edge, one half on each clock pulse. That as I said, every rising edge and falling edge, the rising edge is a half clock pulse, falling edge is a half clock pulse. So together rising and falling will constitute the single clock. So in the single clock, 2 times the data will be transferred. That is a double. So double data double rate will be there in a DRAM cell, that, right? So the DDR2 and DDR3 also there. You might have seen the configuration of the whatever the laptop or computer. So you might be observed there. So that is a DDR2 will be there and DDR3 will be there. So these increase this factor into 4. So DDR will be increased to 4. So DDR will be just DDR will be 2. Just the single SDR will be 1. DDR will be 2. DDR2 will be 4. Right. So DDR3 will be 8 respectively, delivering 4 word, 8 word, burst over 2 and 4 clock cycles respectively. So I hope you observed that DDR compared to the SDR in most of the olden time, that over the CD there was the configuration called SDR DDR may be printed, right? So that shows the data rate transmission, right? Also the DDR, SDR, DDR, DDR2, DDR3. So this will be the first the number of bytes will be going to be increased in a burst, that is. So the internal access rate is mostly unchanged, but each access transfer more data. Internal access rate is unchanged, but each access transfer the more data. So continuation of this, there is a static memory 2 MB. So implement the memory unit 2 MB, that is a 2 power 21 words will be there. So 32 bit each words, so 32 bit each will be there. So they want to organize. So 19 bit internal chip address will be there. So 19 bit. So 19 bit chip address will be required. We can have that. So available chips are 512K into 8. So this is a 512K into bit. So in order to identify this 512K, we need a 19 bit address, right? 20 bit for 1 MB. So minus of that, minus of or half of the 1 MB is a 512K. So in order to uniquely identify the 512K locations, we need 19 bit address. So that is the 2 power 19 is equal to 512 kilobytes. That is and one chip, that is a chip selection will be there, and the 8 bit data will be there. So this will be a 512 into 8, that is a 8 columns are there, sorry, 8 bit data in and out will perform. So this is the layout of the 512 into K memory chip, 512 into K memory chip. So here we want to construct 2 MB using 5K 512, that is, this is 512. So sorry, this is 512, it's not 5K, this is 512K into 8, right? So make it correction. So 512 into K8, using 512 into K, we need to be construct 2 MB. Other words, we can say that 512 is a half MB. Using a half MB, construct 2 MB. So 512 into K in terms of MB, we can say this is half MB. So for such half MB is required to construct a 2 MB memory, right? So 2 MB memory. So total 2 MB, 21 lines is required. So in which the available chip is 512. To identify this 512, we need 19 MB, right? 19 bits. So total 21, 19 will be for this, and another 2 will be used for decoder, right? So 19 bits are used to access the exactly byte location inside the selected chip, right? So inside the ear, 19 bits is required inside this. So not inside the 2 MB, right? For such it is required. So here 21 bit address will be generated, that is A0 to A20. A0 to A20. So A0 to out of A0 21, so 19 bit is essential now, right? Because 512 chip is there now. So in order to identify internal locations of this 512 into K, so we need 19 address lines, that is A0 to A18. So that is A0 to A18 will be there. So those are address. So this 19 bit address we are put here. So right. So I hope it is clear. So similarly we can have. So there is a such chips we can have. So this will be for what is that? For first byte 0 to 7, the data of first byte. So similarly they are telling 32 bits. So that is a 4 such is there. So each column consists of 4 chips. Each column consists of 4 chips implemented 1 byte position. So this is 2 MB into 32. So 2 MB into 32 in order to construct. So using the half MB into 8. So that 4 such chips will be there. So this is half, this is half, this is total 2 MB. So this is one column will become 2 MB of first byte. 2 MB of first byte. So here 32 means 4 byte, no? 4 byte. So here out of 4 byte, the first byte will be coming here, right? Similarly, the last byte. So last byte, this is called 32. That is so here the total 21 address lines are there. Out of 21, 19s are already using here in order to identify the internal location. So remaining 2 we can use for the decoder, right? So remaining 2 you can the MSB, most higher bits of that address, will be used for this chip identification. So that is a 2-bit decoder. So we have using 512 into 8 single memory chip, we can formulate that is. So this is each one is a 512K into 8 memory chip. So a chip is selected by setting its chip select control line to 1, right? So chip site control to 1. Selected chip places in its data on the data output line. So output of others will be there. So there is a second byte is coming of 32 bit total length. First byte, second byte will be there, and third byte will be there, and fourth byte will be there, right? So from here we will get D0 to D7 of 2 MB. So D8 to D15 of second of 2 MB. So D16 to 23 third byte, and 24 to 31 is the last byte, right? So first byte, second byte, third byte, fourth byte. So altogether 32 bit information we can drive out or put it to here. So each cell will be 512 into 8, 512K into 8. So in order to identify that 512 internal all locations, to the how many address lines is required? 19 address lines. So 2 power 19 is equal to 512K, right? So here total 21 address lines are there. Why you want to 21? Because we want to 2 MB. So 2 MB into 32 bits. So for such case 512 into 8. So there is a 16 chips are there. 16 chips are there. So first 4 chips for the first byte, second 4 second byte, third 4 fourth, like so on, that is. So this is a huge amount of memory we are able to construct. So I hope you following that. So organization of the memory of 2 MB into 32 using 512K into 8. So using 512K into 8. Chips are in high impedance state. So 21 bits address a 32 bit word. and dynamic memories. Large dynamic memory system can be implemented using a DRAM chips in a similar way to static memory. Placing a large memory system directly on the motherboard will occupy large amount of space. Placing a large amount of memory system directly on the motherboard will take more space. Also, the such arrangement is inflexible since the memory system cannot be expanded easily. The arrangement is inflexible. Packaging thoughts have led to the development of larger memory units as single in uh, single in line memory modules, single in line memory modules. So dual in line memory modules, right? So packaging of this large huge memory can constitute as a SIMM or DIMM. So memory modules are an assembly of memory chips. Memory modules are an assembly of memory chips on a small board that plugs vertically onto single socket on the motherboard, right? So single socket on the motherboard, so occupy less space on the motherboard. That assembly memory chips small board plug into vertically, so allows for easy expansion by removing that. So controller recollect the information about dynamic memory chip. To reduce the number of pins, multiplexed address are used. Multiplex address are used, that is. Address is divided into two parts. What are those? High order address bits and low order address. So they are provided the first latch using or row address signal, row address strobe signal. So low order address bits selected to column address, so that is a column address strobe signal will be there. However, processor issues all address bits at the same time. All these bits will be generated from the processor. So once it generated from the processor, the memory related aspects, that memory controller will going to split this address into row and column. In order to achieve that multiplexing, the memory controller circuit is inserted between the processor and the memory. So that memory controller will be sat between this processor and memory. So we have a processor and the memory, right? So this processor, we have the data transmission will be take place, that is a direct lines will be there, that is a data bus. So in between that, the controller, the held responsible person to receive the information from the processor and make to understand that memory, how this, what is this address data and so on. So that is a 4 signals will be normally generates. Those are address and the clock, read write active symbol and request. So this I'll release to the memory controller, and there is a row column address. So that is a row address strobe will be there, right? So row address strobe will be there. So that is a column address strobe, read and write part, chip selection, clock signal, right? So chip selection, multiple chips are involved in a memory. So which chip is need to be activate, so that signal. In order to trigger them, clock is required, read and write, and latching that address strobe and column address will be there. So from this we understood to construct up the large amount of memory, that is various aspects we see in that, latency, bandwidth, data rate, and all those aspects. In the similar way, static dynamic memory we can construct as constructed dynamic the static memory. So those principles we can exercise here to perform those aspects. So read-only memories, that S and DRAM chips are volatile, so lose the contents when power not there. The volatile, as long as the power is there, data will be remain. So many applications required such device to retain contents after the power even off. So majority of the applications during off also that data need to be maintained. Example, system on, the OS must be loaded from the disk into the memory, right? So for which the non-volatile memory is required. So that is a read-only memory. So RAM, so that is a hard disk will be there, right? So store instructions which would be load the OS from the disk. So that OS will be there in the disk even for went off, even the switch off mode, OS will be there. When you switch it on, the copy of the OS, the replica of that OS will be play a role to install the OS and it tells to open it, and that will bring. Need to store these instructions so that that will be that will not be lost after the power off. Even after no power, it will be there. When we need to store instructions into non-volatile memory, right? So non-volatile memory is read in the same manner as a volatile. Separate writing process is needed to place information in this kind of memory. So normal operation involves only reading of data. So normal operations involved only reading of data. So this type of memory is called read-only memory. That is a read-only memory will be there. So read-only memory, data are written into read-only memory when it is manufactured. Programmable read-only memory. So we can program to store the data into that read-only memory. So it is a programmable. So program to write the information or read the information or delete the information, allow the data to be loaded by the user. Process of putting the data is irreversible, right? Putting the data is irreversible. So storing a kind of information specific to user in a read-only memory is expensive. So specific to the user is expensive in the read-only memory case. So providing a programming capability to user may be better. Providing a programming capability to user may be better. There is one more kind of read-only memory, that is erasable programmable read-only memory. So the programmable read-only memory is irreversible, you cannot delete, that is. So erasable programmable read-only memory, it is both options are there. Store data to be erased and new data to be loaded. So that can be performed. Flexible and essential to during the development phase of the digital system. Erasable programmable read-only memory. So erasers requires exposing the read-only memory to UV light. That is, UV means ultraviolet light. So it will be exposed to the ultraviolet light and data will be erased, that is. So electrically erasable programmable read-only memory. Read-only memory, programmable read-only memory, erasable programmable read-only. Now electrically erasable programmable read-only memory, that is a EEPROM. EEPROM. To erase the contents of the EEPROM, they have to be exposed to the ultraviolet light, right? So that will help to delete the data. Physically removed from the circuit, EEPROM, the contents can be stored and erased electrically. So storing and erasing is electrically possible. Flash memory. So flash memory we have as a similar approach to EEPROM. So read the contents of the single cell but write the contents of the entire block of the cell. Single cell you can read, writing you can write in the block wise. So there is a burst is reading, and block is block wise is writing. So that is operations. Flash devices have greater density, so there is a huge capacity of that memory, higher capacity and low storage cost per bit. So power consumption of flash memory is very less, making it attractive for use of equipments that is battery driven. So that is a battery driven, so it is a low cost will be there, and huge amount of memory we can keep. That is, single flash chips are not sufficiently large, so large main memory modules are implemented via flash cards and flash drives. So speed, size and cost, there is a challenge for the architects, the designer of the system, to provide enough large memory. A reasonable speed at an affordable cost is a either very important, and it's a commercial aspects, and most of the user will expect that. So static RAM, very fast, but it is expensive, and more power will be required because the basic SRAM cell has a complex circuit, making it impossible to pack large number of cells onto single chip. You have seen that two transistors is required at the minimum, and the diodes are merge those and form a cell. So having so definitely that could be size is more and expensive, and what we can say that the density is very less, right? So area is more, so density is less. Dynamic random access memory we have seen simpler basic cell circuit, one transistor and capacitor, right? Hence are much less expensive, but significantly slower than SRAM. The accessing is slower compared to the SRAM. So the other alternative, that is a magnetic disk, large memory, huge memory, we can formulate with help of this magnetic disk, that is. So storage provided by DRAM is higher than SRAM, but it is still than what is necessary. Secondly, storage such as magnetic disk provide a large uh, amount of storage, but is much lower than the DRAM. So secondary memory, that is a hard disk, the magnetic disk or tape, provide a large amount of memory storage, but it is lower than the DRAM, right? So memory hierarchy is one of the most important aspects we have to see, because the different devices involved in the systems, the device may be a computation related device, that is a processor, device may be storage, device may be recording, device may be audio video, so on, that maybe input device, output device, maybe display device, printing device, so on that. So these are all heterogeneous the devices are there. Obviously they have heterogeneous speed, their speed is not related to one another. They are achieving a synchronous is a very tough task, for which we need to be understand the memory hierarchy. If you know the memory hierarchy or speed and the data in which they are handling, all those the parameters, if you know very well, so we can make it our hierarchy, we can understand the hierarchy. You are able to understand the hierarchy, then the designer, the design aspects will be able to understand. So from this the hierarchy we can try to, it helps to make a synchronously we can organize that. So at the top level we have, from the CPU premises, we have processor have some memory, so through the registers. So register is a small one word or two word, one register is one word, right? So that depends upon the word length of the that is a 8-bit word, that is a 16-bit word or 32-bit word, so on that. So it depends upon the length of the register, and also it depends upon the architecture of the processor, architecture of the system. So there is a the small memory called cache memory, which is a L1 cache for data or instruction, for string information, so on. That is the fastest access to is data is held in the processor register. So registers at the top of the memory hierarchy, because they are electronic device, so they are flip flops, so they are basically fast. uh, the relatively small amount of memory can be organized on the processor chip. This is a processor cache. So cache memory is there. So somewhere in the previous discussion we discussed about the speed of the processor and the memory is a mismatch, because processor handling the data in terms of the byte or word, memory handling the data in terms of the blocks or several words. So there is a size gap, and also processor deals in terms of the picoseconds or nanoseconds, whereas memory deals in terms of the milliseconds or seconds. So there is a speed gap between these two. So in order to bridge this gap or synchronize the gap, so there is a additional memory is essential, so that is a cache memory. So to adjust the speed gap is a cache memory. To adjust the size gap will be a virtual memory. So that will be discussed in the subsequent discussion anyhow. So that is a secondary cache, that is a L2, one for instruction, one for data, so on. That is, so we have a main memory. So two levels of cache, that is level 1 cache is the processor chip, level 2 cache between the main memory and the processor. So the level 2 cache which that is. So we have a magnetic disk secondary memory, So we have a next level is a main memory implemented as a SIMM, much larger but much slower than the cache memory. So much larger, much slower than the cache memory. So can I have that is so the next level is a magnetic disk, that is hard disk in our system, right? So hard disk may be in terms of several GB. We have seen that in a CC camera, that may be several TB will be there. Huge some inexpensive storage will be there. So speed of the memory access is a critical. Speed of the memory will be access is a critical, that is. So idea is to bring instruction and data that will be employed in the near future, to bring instructions and data. So already most of the systems are available, handling differently or simultaneously. In most of the microcontroller case, both data and instructions will be put it in the same memory, whereas the microprocessor will treat them in a different compartment. So that is for most of the general purpose application. For specific applications such as the airbag in a car, such as weighing machine, such as microwave oven, right? So those have specific application. In that case, microcontroller will be taken place. So microcontroller always put this instruction and data in a single memory and handle them, right? Because the less amount of data and instructions will be there, so that will be repeatedly performed. So that will be stored in a memory, right? So that is a speed of memory access is a critical aspects for some of the application. So here we have seen that processor, register, and the memory. We have a cache memory and secondary memory and main memory, and we have a magnetic disk, and apart from this we can have also the tape, drum, and also we can connect to server. So server, right? Server is a huge amount of memory, and internal, even beyond that, the weather forecasting and pharmaceutical analysis and various DNA analysis, so on. That is, so beyond that, satellite images, satellite information, the server may be connected to satellite. So there is a other maybe IoT applications. So in that case, hierarchy of the memory is the most important. So if you know this hierarchy, then in the same hierarchy we can exploit the potentiality of their each memory speed and size. So that maybe helps to exploit or encache or make use those potentiality in a same performance, in the same performance we may expect. So in that case we need to be exercise and can impose those memory hierarchy to expect some good performance. So from this, so here we have increased the size will be increased from the higher to lower. So we have the speed will be increased from bottom to top, that is secondary disk to processor register speed will be increases, and the cost is also increases. From magnetic memory you can your pen drive may be very cheaper, so whereas the main memories are very costlier, right? So the speed and cost will be increases from magnetic disk to processor register. So the size will be decreases, that size will be increased from processor to secondary memory, right? So this is a hierarchy of the memory. So from this I hope you will be understand the concept of this large memory construction and different type of memory and various aspects related to this memory design. Thank you for patient listening of this topic, large memory and different type of memory. Again, the books are Carl Machar et al. That is a computer organization by Fifth Edison, Tata McGraw, William Stalling, computer organization and architecture by that Pearson Education. Apart from this, there are also some books are there, and also some internet or magazines we can refer. Thanks to coordinator, moderator, and subject expert. So thank you. So you can post the queries to bhaj3nu@gmail.com. Thank you once again. Thank you one and all.